Many different physical system can be modeled as a DFA. So we started with that light bulb thing and modeled it as a DFA, a very simple DFA. But here is a very common way to visualize a DFA as a machine. So when we think of a DFA, at the back of our mind we have this sort of a computer. Okay, so it's like the inputs are written on a semi-infinite tape, or just say it's written on a tape. So the tape is divided into different cells, and each cell contains one symbol, one input symbol, right? And this computer, so this has a read head. So at any point of time it is looking into one symbol, and this computer contains a program which is nothing but the transition table. So this kind of acts like line number, if you like, and this entire thing is sort of a program to this computer, and it has a finite memory. So this finite memory corresponds to the fact that it has finite number of states. So and this machine reads the input one by one, starting from one side and then moving say from left to right, and at each step, according to this program, it changes this data which is written in its finite memory. So this is sort of a variable that it maintains. Okay, so this is where it starts. So this is this Q0 is the start state. So initially it has this Q0 stored, and then it says 1. So its program tells it to jump to this line. Okay, so this, so this is what happens in the next step. So this was the first state, and now the tape has moved, or the head has moved, and it is looking into the second symbol, and also the control has moved into say this line. So now it's in state Q1, so which is stored in this finite memory, and again depending on the symbol it will make the next move. So here it will make the move to Q0. So, and this way it just keeps on executing this program. It updates this variable sort of thing which requires finite memory, and after reading all the input, so the last input symbol is read, and then if it comes back to say this state Q0, then it accepts. Okay, so and it moves in just one direction. It starts from the extreme left, and then one by one it moves to the rightmost thing. So this is one generic way of think of our computer, and the other models that we are going to study, this push down automata and Turing machine, so they will be generalization of this picture. So instead of a finite memory, in case of a PDA, it will have some other place to store some data, and that is not finite. Okay, so in fact that will be a stack, if you remember the stack queue from your data structure and algorithm course. So a PDA will have an additional potentially infinite stack associated with this, and Turing machine will also have some infinite place to store intermediate data, its internal data. So those will be generalization of this picture, but DFA is the simplest one. So this was the definition we gave. The automata is just this 5 tuple Okay, and we defined each of these things. Now, in order to formally express the acceptance criteria, we need to define this extended transition function. So this transition function, for our particular example, we talked about this delta hat. So in fact, the same argument works for this general definition of deterministic finite automata, but let's see that in slightly more detail. So if you start from any state, so it's not the starting state like this q0. Suppose you are in some state at some point of time, you are in some state q, and then you process this input symbols, this a1, a2, a3 up to an, right? So that means in this n many time steps, so each corresponds to a time step. So in this n many time step, you have processed this string, okay, which consists of this n symbols, and you change your state accordingly. So you start with this state q1, q, and upon reading this input symbol a1, so you change the state according to your transition function. Suppose you change it to q1, and similarly in the next stage you start with so q1, and upon seeing this a2 as an input symbol, you move to this, say, q2 or whatever, and the final thing is p, right? So first of all, this is a path in the transition diagram, right? So a transition diagram is a directed graph, and if you recall the definition of path, it means a sequence of edges. So and these states are not necessarily distinct, because you see your finite automata has finitely many states. So suppose it has 5 states, right? And this input string can be anything. Say this can be a string of length 10. So you need to make 10 transitions. So you will there will be repetition of states here. There can be repetition of states here, but still you have a path of length n, which corresponds to the string of length n, right? So it's very helpful to visualize the strings as paths. Obviously that path will depend on where you start, but once you fix this q, then this w corresponds to a unique path, right? So this uniqueness comes from the fact that we are dealing with deterministic finite automata, okay? Because each at each step, the next state is uniquely determined. So yeah, each string of length n corresponds to a unique path of length n, provided we are given this q, and these are not necessarily distinct. So then we said it before that, so we want to capture this as this extended transition function. So that means we want that thing to be such that if we provide q here as an argument, and if we provide, say, w here as an argument, so the result should be p. So this should encompass the fact that starting from state q, if I process the input string w, then I should be in state p. And this will obey this relationship, right? So suppose after processing this string w, you are in some state p, and then you make one more transition. So this is just one transition, so that is why I have this transition function delta. So this is not delta hat, right? So this is just one transition, so that is why just the transition function is sufficient. But this part is string, it's more than one symbol, so this is delta hat. So now if I have this part, if we calculate this p according to this delta hat, and then apply this delta one more time with symbol a, so then I'll reach some state r. But by definition of this delta hat, okay, by definition means what we want this to be, because we haven't defined it yet, but at least the thing that we are trying to capture. So that tells us that this thing can also be written as this delta hat of q and wa, right? Because wa is this whole string, so w and then a, so that string wa, so that if we plug in here, so that means starting from q after processing wa, it lands in this state r, which is nothing but this expression. So this p is this one, and then we apply this. So we have this condition for delta hat. And if this part is empty string, so this can be empty string, so then this should be q itself, right? Because starting from q we are not processing any symbol, so this is empty string, and then that means we should stay in this state q. So with an epsilon here, we should have a q here. At least that is what the motivation is. So now this is not a proof, so this is the motivation behind defining this q hat. Okay, so we can take this as the definition of this extended transition function. Okay, so again, this is a recursive definition, so this gives the base case, and then this recursively defines it depending on a w of a string of smaller size. So this has length 1 more than this length, so this recursively defines it for all strings and all q and all all q and all string here, right? So this we can take as a definition, but the definition came from the fact that we wanted to capture with delta hat this sequence of transitions. Okay. Now once we have a formal definition of this extended transition function, we can say that a string w is accepted if and only if this delta hat of q0 and w is in f. So what does it mean? That means informally it says that if we start from q0 and process w, then we should land in some state in this subset. Okay, so if we are in some state in this subset, then we accept this w. So the examples we have seen so far, they contained one final state, so it's actually better to see this with more than one final state. So we'll come to those examples. And this also we mentioned before. So once we define the acceptance criteria and acceptance of string, so then this is the definition for the accepted language. So we say an automata M accepts a language LM, where this LM is all the strings that are accepted by the automata, and this definition is valid for other automatas also. So here we are talking about DFA, so that is why the acceptance condition for string is specifically this. So but in general, the language accepted by automata M is all the strings that are accepted. So as I mentioned before, it is very, very useful to view a string as a path for a given state q. I mean, where you start, and this string uniquely determines a path starting from this q. Okay. So we will draw this paths consisting of multiple symbols as some kind of wiggly line. Okay, so a single transition will be shown as a straight arrow, and a chain of multiple transitions will be shown as this wiggly line. So this is a path corresponding to this string w. Okay, so each w will correspond to a unique path given this state q. Now this picture is very useful because a lot of properties are immediately clear from this thing. For example, if I ask you to prove that if I do this delta hat with q and x, and then again apply delta hat with this and y, then I get q and the concatenation of x and y. Okay, so we can prove this formally, but what is it saying actually? So it's saying that, so what is this what is this transition? So that means that we are starting from q and we are processing this string x. It's a string x, right? So it's in sigma star. So after processing this thing, we reach some state. So this corresponds to this state. So this whole thing, and then again we are processing this y. So then we move to this state, right? So this breakup is about this breakup, and then this whole thing is nothing but we start from q and process xy, right? So this thing, in other words, is just delta hat of q xy. Now if we want to actually prove this thing, so we need to properly write this proof as some formal argument. So I already have it here. So something like this. So so almost always we need induction on input string length. So here we can do the induction on the length of y. So we start with length 0, that means y is epsilon. So that is the basis, and that will be trivially true because if I put epsilon here, that means by definition of this delta hat, this will be this state itself. So it will be this thing. Right? And here epsilon means this will be x itself. So in both sides it will be delta hat of qx. So basis is fine. And then in induction step we write it as za. So this z is shorter than y. So by induction hypothesis we already have this thing, because z is shorter than y, and this was induction. So now we can write this one by the definition of delta hat. We can write and break this delta hat as a delta hat with z and then a delta with the symbol a, and then by induction hypothesis we can club these two together in xz, and then we have the symbol a and delta here, and again by definition of delta hat we can club this delta and this delta hat together in this xz and a. here. So these and this follow from the definition of delta hat, and this follow from the induction hypothesis. So this is what a formal proof looks like. So if you are asked to write a proof, then that is what you should write. But I mean, that's not how we solve it mentally. So mentally we always have some kind of a visual representation. So this is what the visual representation is. It's very helpful. Okay, so one thing I should emphasize, that I'm telling that this W corresponds to a unique path given this Q, and this uniqueness comes from the fact that our automata is deterministic, right? So for DFA only, this will be a unique path. But for NFA, again, we haven't defined NFA like we properly defined DFA. But from those examples, you saw that in a single step, so even when we know the current state and the current input symbol, we do not know what exactly will be the next state, right? So suppose you are here and you see some input symbol, then you can move to some state here, some state there, and this will be true for this long chains also, right? So they can intersect, they can be like tree like thing, or so anyway. But the point is, for non-deterministic automata, this paths, there won't be any unique path. So there can be many paths, and it can lead to many different states. So that is the difference between deterministic and non-deterministic automata. So again, we come back to the example we discussed before, and once we have the formal definition of Q hat, and we write our acceptance criteria in terms of Q hat, we can formally show that this string is accepted by this automata, right? Because for example, what is this value? So by definition of delta hat, it will be delta of this delta hat and then this input symbol. So this will be just this part, and then this. But this we can compute here, okay, with the help of this and the delta, the transition function for this and this. So in fact, starting from here, we first compute this and so on. So yeah, so this is what delta hat is, and this is how we formally express the acceptance criteria, and the language accepted by this thing comes from there. So few examples we should discuss. So first of all, I was itching to give you an example with more than one final states, because that is important. So this is also very simple, because we are using only one symbol. So our alphabet again consists of only one input symbol, and this three states. So you see, again, this a to the n. So a to the n means a concatenated n many times. So this you can think of as encoding of the integer n in unary form, right? And you can see that with a to the 0, that means epsilon, you are here, then a here, a square here, a cube, again you come back here. So again a4 here, a5 here, a6 here. So that means this state corresponds to the multiples of 3, right? So if you feed a to the 6, a to the 9, a to the 12, you will come back here, and then this will corresponds to some a to the I, where this I, if you divide by 3, will give you remainder 1, and this will give you remainder 2. So for example, if you take a to the 4, you will be here. If you take a to the 5, you will be here. So that means this automata accepts all this a to the n such that this n is not divisible by 3. Okay, so here we have two final states, and we can have automatas like this. You see, there is no path from the starting state to the only final state that we have here. Okay, so there is no way to reach this thing. So what will be the language? So it doesn't accept any string, right? No string can give you a path from here to here. So the language is empty. So there is no string here. It's not the empty string, right? Because language is what? Language is a set of strings that are accepted by this machine, but this machine doesn't accept any string, so the language is empty. So as I mentioned, we also saw this example before, that the starting state can also be a final state. So here we have two final states, and one of that is a starting state also. So this sort of thing, if can be, this set of final state if can be anything, any subset of Q, set of all states. And those were with alphabet only A. Here we have some more complicated examples with alphabet A, B, and so this, I can tell you that this is an automata which accepts all the strings which has odd number of A's. So this should be odd number of A's. This should be odd number of A's, not odd number of ones. Okay. So just make this correction. Why? Because you see that this state corresponds to even number of A's, and this corresponds to odd number of A's. So you can have as many B's as you want, but once you have A, you move to this side, and then again you can have as many B's as you want, but on a second A you come back here again, perhaps some B's, and then again on third A you come back here. So you see that it doesn't matter how many B's you are processing. So if you are here, that doesn't change the state. If you are here, that doesn't change the state on B. So B doesn't change any state. The only thing that is happening is that it's changing state on A, and then it's basically our this light bulb example. So but here we have two alphabets, slightly more general version of that, and this is more complicated to come up with. So if I just give you this language, that okay, so what is this language? This is the set of all strings that end with this pattern AB. So AB are symbol. So this two particular symbol A and B. So this W can be anything. Okay, this can be empty also. So that means what are this form of strings? So these are precisely the form of strings which end with AB, right? So all those strings that end with AB. So it's in LM if and only if it ends with AB. So if I just give you this language and ask you to come up with a DFA, it will take some time. At least you have to think slightly. It's not at the tip of your pen. So in fact it's a good exercise. So just pause this video, consider this language, and without looking at this diagram, try to come up with a DFA which accepts this language. So it accepts a string if and only if it ends with AB, and you will see that it's not entire. It's not completely trivial. You have to think a bit. But anyway, these are examples of automata. So one hint I can give here is that you see in this automata, no matter in which state you are, so suppose you are in Q0 after processing something, so after processing W, see you are in Q0, and then if you process AB, then you will come to Q2. But you may not be in Q0. After processing W, you can be in Q1. But then again, from here, if you again process A and B, you will be in Q2. Similarly, if you are in Q2 after processing W, so then again after processing A and B, you will be in Q2. So no matter what W is, for WAB, you will always be in Q2. But that only proves that this right hand side is a subset of LM, right? Because this argument that I gave is saying that if the string is of this form, then it will be accepted by this automata. You have to prove the converse also, right? That if a string is accepted by this automata, then it is of this form, and that is also kind of easy to see, because see, if some string is accepted, then after processing it's in Q2, right? So in order to reach Q2, it has to come from this state, because there is only one incoming arrow, and in order to reach this state, so either it has to take this arrow or this arrow in the previous symbol, right? So something which is accepted leads you here. So the last symbol of that accepted string, you know, that is B, and before B it has to be this A, right? Otherwise you cannot reach Q2. So this in some sense proves, but again, if I ask you to prove, if anybody asks you to prove, you need to write a formal proof, right? Not and one last thing I want to mention is that, see, what is the language here and what is the language here. So here both states are final states, so it doesn't matter how you process and where you are. Okay, you process any string, so you will be either in Q0 or Q1, and both are final states. So any string you are given, that will be accepted, right? So the language is in fact the set of all strings, right? So this is the alphabet, and this is the set of all strings that you can construct with this alphabet, and this is the language accepted by this machine. But if this is the language, we have a simpler machine which can do this. So with just one state, right? On both this input symbol A and B, it just comes back to itself. And again, this is simple. So you see that there can be two different automata, two different DFA, say, accepting the same language, but this one is simpler, right? So then we ask that, given some DFA, can we determine whether it's the simplest one, or if it is not, then can we come up with a simpler one or the simplest one, and this sort of thing. So we will cover DFA minimization in detail later.